Hello and welcome to today's video where we'll be talking about the basic laws of logic. So these are rules that are used to help make solving complex logical equations simpler. So they're basically just kind of definitions that turn things like double negation right here into just one letter or one connective. So it's a way to simplify connectives. Hello and welcome to today's video where we're going to talk about the basic laws of logic. So these are really important rules that help make complex logical questions a lot simpler and easier to solve. So these are just things that can turn things with a lot of connectives into things with just a few connectives. So these are important to know and things you're probably going to want to memorize if you have a class in discrete math or just really wanting to understand this. So as you remember, a tautology and a contradiction. A tautology is a logical statement that's always true, and a contradiction is the opposite of that, and that's a logical statement that's always false. And for this video, assume that the letter T, capital T, is tautology, and capital F is contradiction. Think of F just like false. It's always false. So let's get into these laws. They're pretty intuitive. A lot of the times you're kind of understand what the simplification is going to be before I say it. So if you want to, you could pause it and try to think about it. First one, double negation, pretty simple. If I have not P, that means I'm the opposite of not P, and if I'm the opposite of not P, I'm just P. So that's equivalent to just P. So if I would never need to say not P, because I could just put the letter P, and that's a lot simpler. And for this video also, like P, R, and Q, they're all just propositions. So now let's talk about identity laws. And all identity laws in math are just things that, think about the identity law of multiplication, the identity law of addition. It's if you multiply by something by 1, it equals itself. That's the identity for multiplication. Then if I add 0 to something, it's still itself. So this is going to be similar here, right? Because identity means that it equals itself. And let's look at the first one, P and true. So if something, tautology, true. So if something is always true and I'm saying, well, P and that something, that's just going to end up being that something, right? Because if something else is always true, then the anchor, the only thing that's going to make it false is P being false. And then on the flip side, really the same thing, P or a contradiction. So if I'm saying either P is true or this other thing is true, but the other thing is always false, I really just have P. So hopefully those two make sense intuitively. So identity laws, they're always going to equal themselves. So now domination laws. These are kind of on the flip side of identity, where identity, the proposition kind of controlled the outcome. Well, this is going to be the opposite. So now the tautology and the contradiction are going to control the outcome in all scenarios. So look at the first one. It says P or true. So remember, with P or with the or command, or connective in this case, it means that P is true or the other thing is true. And if this is always true, we know this is going to be true no matter what. It doesn't matter what P is, this statement is going to be true. On the flip side, if I have P and a contradiction, the only way the and command can be true is if both are true. And if I have a contradiction, it's never true. So the answer to this one's just going to be false all the time. So now we have De Morgan's laws, and we actually did prove these in an earlier video, but now we're just going to practice just knowing the law and being able to understand what it means. So not P and Q, if you remember, this ends up being not P or not Q. So if we have the negation of the whole thing, not P or not Q. And what we actually do, the way I like to think about it, I'll write it out here, so not P and Q. You actually kind of distribute the negation to the P and the Q, so that becomes not P and then not Q, right, just from the distribution. Then I like to think that I also distribute the negation to the connective. So if I'm not and, then I must be or. It's kind of like the opposite. So you kind of do the opposite of everything and you get not P or not Q. So that's what I do for De Morgan's laws when we have a negation and then something in parentheses. And we can actually use the exact same logic here. So not P and Q. Well, I'm going to distribute the negation to both the connectives, and I get, well, it's not P and then not Q, right? And then now what's in the inside? Got to distribute to the connective as well, and I'm the opposite of the and, of the or, so I must be the and. So that's the same as not P and not Q. And you can prove that using truth tables, which we have done in the past. So hopefully these rules make sense, and now we're going to look at some examples of how these rules actually apply and how they can help you out with some problems. So in this first one, we're going to use the logic laws to simplify the statement P and F and Q or T. So I like to take it one step at a time. So let's start with P and F. So P and F, if I have P, which is some proposition, and a contradiction, if it has to, that means P and F, that means that both have to be true. Well, the contradiction can never be true. So that's the same as just saying F. And if you remember, that is our domination law. That's one of our two domination laws. Okay, so I have F false. I know that that's equal to F. And then I have and that's equal to Q or T. So I'm going to try to simplify Q or T, see if I can. Okay, so Q or T. Remember, this is saying as long as one of these two is true, this will return a value of true. And if I have the tautology here, the T value, that's going to be always true. So this is also domination because T is always going to be true, and that's going to make Q or T always be true. So that's going to be simplified to the true, and I'm left with false, a contradiction, and true. That can never happen. You can never be, if you have a contradiction, the and is always going to be nothing. So the answer to this is just a false. It's just a contradiction. So this whole thing could simplify to a contradiction. So never going to be true here. And really, I could have quit once I got to this step. When I saw that the first part was false, and then I saw it was false and something else, it didn't matter what the something else was. It had to be false because if an and implies true only when both are true, and I know the left side's never going to be true. So this whole thing is false. Alright, so let's look at another one. Use logic laws to simplify the statement. We have not P, and not Q. Okay, so what I'm going to do is I'm going to use, I see that this kind of looks like a De Morgan's law, so I'm going to do that distribution property here. So I'm going to distribute it to everything, the not symbol, so the negation. So it's going to be not P. Then I'm going to switch my connective, because that's what we do with the De Morgan's law, becomes not Q. Okay. And remember this rule with double negation, we've got two examples of double negation now. So what is not P? Remember that was just P, pretty simple to see that one. Then or not Q is the same thing as Q. So this whole thing simplifies to P or Q. So I can take that pretty confusing logical statement and simplify it to just simply P or Q. And hopefully that makes sense. So hopefully now you kind of understand these four basic rules, nothing too difficult. We'll get into some more confusing, unique ones in the next video. If you have any questions, don't hesitate to contact me. Thanks for watching.